Welcome to The Explainer. You know, in science and engineering, we face this massive challenge, right? How do you accurately simulate the real world? I'm talking complex physics, without needing a supercomputer the size of a small country. Well, today, we're diving into a really smart technique that does just that.
All right, so here's how we're going to break it down. First, we'll tackle the core problem. Then we'll get into the physics-based approach for modeling it. After that, the really cool part, how to find and fix errors intelligently. We'll look at some real examples, and then wrap up by talking about why all this efficiency is such a game changer.
Okay, so let's jump right in. What is the fundamental challenge here? What's the thing that keeps so many scientists and engineers up at night?
It really comes down to this. How can we accurately simulate super complex physics without needing, infinite computing power? Think about trying to model the airflow over a jet wing or the intense front of a combustion flame. You're immediately hit with this classic trade-off. Do you want it to be accurate or do you want it to be fast? Getting both is the holy grail.
A huge part of the problem comes down to these things called singularities. Now, don't let the name scare you. Just think of them as hotspots, tiny regions where conditions are changing like crazy. Imagine the immense pressure right at a wellhead, or the razor-thin edge of a shockwave. That's where all the action is.
And here's the dilemma. If you use a standard, uniform grid to model this, you're stuck. If the grid is too coarse, you just completely miss those critical details. It's like trying to see a tiny crack with a blurry camera. But if you make the entire grid superfine to catch everything, well, you'd need an insane amount of computing power. It's just not practical. So clearly, we need a much smarter way to do this.
All right, so how do we get smart about it? The foundation is a modeling approach that's actually built for these kinds of physical problems from the ground up.
And that approach is called the finite volume method, or FEM. What makes FEM so powerful is that it's deeply rooted in real-world physics. See, instead of just crunching abstract math, it divides the whole problem space into these little control volumes. Think of them as tiny boxes. Then, it meticulously balances what flows in and what flows out of each box, making sure fundamental laws like the conservation of mass or energy are never violated. It's this direct link to physical conservation laws that makes it so robust and trustworthy.
Okay, so when you're setting up the geometry for an FEM simulation, you've got a couple of main options. You can store your variables right in the middle of each grid cell. That's the cell-centered approach. Or you can store them at the corners, the nodes where the grid lines intersect. That's the vertex-centered approach. For what we're talking about today, we're going to focus on this vertex-centered setup. It has some really nice properties that make the next step, the smart adaptation, work beautifully.
So we've got our method, the finite volume method, but we still haven't solved that original problem of the inefficient uniform grid. This is where the magic really happens.
Instead of that brute force approach, we get smart. We decide to focus our computational firepower only where it's needed most. I love this analogy. Think of the simulation grid like a smart camera. It automatically zooms in and increases its resolution on the most important parts of the action, while leaving the boring parts in low res.
But how does the camera know where to focus? That's the key question, right? Well, we use a technique called a posteriori error estimation. It sounds complicated, but the name literally just means after the fact. Here's the idea. You run a quick, rough calculation first. Then, this technique acts like a diagnostic tool. It scans the results and flags the specific spots on the grid that are causing the most inaccuracy.
And it all comes together in this beautiful, adaptive loop. Check it out. Step 1. You solve the problem on your current grid. Step 2, you calculate those local error indicators to see where it's messy. Step 3, you identify and mark the cells with the highest error. Step 4, you refine. You subdivide only those marked cells, making the grid finer just in those spots. And finally, you repeat the whole process. Solve, calculate, identify, refine, over and over. This loop is the engine that drives the whole smart simulation.
Okay, that's the theory. It sounds great, but what does it actually look like? Let's check out some practical examples from the research.
So for our first test, we're simulating a simple Gaussian curve. You can think of it like a peak concentration of heat or something. And as you can see, we start with a very basic, very coarse, uniform grid. Nothing special here. But now, look at this. After just 3 loops of that adaptive process, the grid has completely transformed itself. The algorithm automatically figured out where the curve was changing most rapidly and piled in the detail right there. And just as important, it left the flat, boring areas alone. That is efficiency in action.
All right, test 3.
This is a classic problem in fluid dynamics, capturing a sharp boundary layer. This happens when a variable, like velocity, changes super fast right near a surface. And again, look what the algorithm does. It just instinctively zooms in, creating this incredibly fine mesh right at the boundary to capture that steep change with total precision.
And one more for good measure. This is a simulation of groundwater flow. You can see how the refinement automatically clusters near the sources and the boundaries, exactly where the physics gets complicated. It's just smart. It puts the effort where the problem is, ensuring an accurate result without wasting a single calculation on the easy parts. Okay, so we've seen the theory and we've seen the pretty pictures. They're compelling. But what does this all mean? What's the big picture impact of all this? Well, the impact is absolutely massive. You get faster calculations. Simulations that might have taken days can now be done in hours. You get higher accuracy, but with way fewer computational resources. And that, of course, saves money, saves energy, and reduces the need for giant supercomputers. But the most exciting part? It lets scientists and engineers tackle problems that are way more complex, more realistic than what was ever possible before.
I love how the source paper puts it. They say a posteriori error estimation provides a tool for the self-adaptation of the mesh. And that's really the perfect way to describe it. We're giving the simulation a kind of intelligence, the ability to look at itself, find its own flaws, and then fix them. It's pretty incredible.
And that really leaves us with a fascinating question to ponder, doesn't it? With smarter simulation tools like this, what previously unsolvable problems are we going to tackle next? By making our methods more intelligent, we're literally pushing the boundaries of what's possible in scientific discovery. Thanks for joining me on this explainer.